Welcome to the Unit 5 Day 1 notes. Go ahead, pause the video and work out this warm-up problem, remembering all of our theorems about parallel lines cut by a transversal. So when you're done, unpause it and see how you did. So for this first one, we have parallel lines cut by a transversal, and we have same side interior. So they are not congruent, but they are supplementary. So 2x plus 38 plus 5x minus 5 adds up to 180 degrees. So I have 7x plus 33 equals 180. Subtract 33 from both sides. Get 7x equals 147. So x equals 21. If I were to plug this back into both of these, 2 times 21 is 42, plus 38 is going to be 80. 5 times 21 is 105, minus 5 is 100. 180 together make 180. So the reason we bring up parallel lines cut by transversal again is because this chapter we're going to start off talking about parallelograms. Okay, parallelograms have the word parallel in them. That's going to be kind of important. A parallelogram is a quadrilateral all that means is that it's got 4 sides. But it's a quadrilateral with 2 sets of parallel sides. So breaking down the word, quad is what gives us the 4. Lateral is what gives us sides. Parallelogram, we have 2 sets of parallel sides. Now to show this, we use these arrows to say those 2 sides are parallel. You cannot say these 2 sides are parallel like this, because what this indicates is that every single one of those sides has the exact same slope and would never run into each other. However, these clearly run into each other there and at all the corners. So to make sure we differentiate that a little bit, we put 2 arrows to say that these 2 are parallel, those 2 are parallel, but these 2 are not parallel. So our very first theorem about parallelograms says that opposite sides in a parallelogram are congruent. So the parallelogram, we already know that these things are parallel. That's what we know, just by it being a parallelogram. What this theorem also tells us is that AB and DC are congruent sides, AD and BC are congruent sides, and again, these things are not guaranteed to be the same, so we have to use different markings. So 1 mark here, 2 marks there. Okay, we'll get into special cases later, but not right now. All right, so we're going to prove that. We are going to prove that opposite sides are congruent in a parallelogram. So we're going to start with our statements and our reasons. These proofs are going to be a little bit longer because we keep adding on to what we've done previously. All right, so step 1, ABCD is a parallelogram. That's how I'm going to abbreviate parallelogram. Parallel lines hyphen gram. That is given to us. Okay, anytime we use a vocab term, we need to use a definition of that vocab term. So my reason for the next one is definition of parallelogram. The definition of parallelogram, that quadrilateral has 2 sets of opposite parallel sides, tells us in this case that segment AB is parallel to segment CD, and segment AD is parallel to segment BC. So I've got those markings. Now step 3 is one that we may have not done before. We're going to draw in segment AC. Okay. The reason we can do that is between any 2 points, we can draw a line. 2 points form a line. Now the benefit of doing that is now I've split this thing into 2 triangles. So now I can use all of my theorems that we talked about previously. So I would start with segment AC is congruent to segment AC by the reflexive property. So I've got that right there. Now I can say angle, or number 5, I want to say something about these angles that are just formed. But I have parallel lines cut by a transversal. That's what we just made happen. So step 5, I'm going to say that angle BAC, I can't just say angle A because I could be this angle or that angle or the original full angle. So angle BAC is congruent to angle DCA, because if we have parallel lines, then alternate interior angles are congruent. So BAC was this one, and then DCA was that one. It might be tempting to say something about right angles here, because you look at this and go, oh, it's a rectangle. We can't say for sure that this is 90 degrees, because it might be 91. It could be 90.1. We're not guaranteed anything about it being a right angle. So we just have to go with what we've got. So far, we've got an angle in each triangle and a side in each triangle. I'm trying to prove the opposite sides are congruent, so I can't find anything about sides to prove these triangles are the same. So I have to find another angle. So step 6 is going to be, I probably could have done this in step 5 actually, but I'm going to do it in step 6. I'm going to say that angle DAC is congruent to angle ACB for the exact same reason. That's why I said I could have done it in step 5. All right, but now for step 6, like step 5 was the highlighted pieces. Step 6 will be these highlighted pieces where we have these parallel lines cut by the transversal. All right. You have to look at it slightly differently, because if AD and BC aren't parallel, you would not be able to say this next step, step 6, to say that these are, in fact, congruent. But because those lines are parallel, we can say that. That gives us another set of angles. So step 7, I can say triangle ACD is congruent to triangle CAB. I'll make sure I get my angles right. ACD goes from here to there to there. CAB, that looks pretty good to me. Step 7, the reason I can say that was angle side angle congruence. And now, to show the opposite sides, I have one final step, step 8. I'll do this in one step. Segment AB and segment DC, and then segment AD is congruent to segment BC by corresponding parts of congruent triangles being congruent. There is a lot in this proof, in this problem. But ultimately, this is just all of the various pieces of proofs we've used so far. Okay, we used a couple of new things, like definition of parallelogram. That's brand new. 2 points form a line. We used that back in Unit 1 before we even knew what a proof was. Reflexive property we've been using. If parallel lines cut by a transversal, we used an entire chapter. Prove triangles are congruent, we used an entire chapter. CPC-TC was that entire chapter. Okay, so we're just continuously building on. So it's a long process, a long set of steps, but it's just slowly building up. Generally speaking, in geometry, when in doubt, try to prove two triangles are congruent. So for this next theorem, it's very, very, very similar. It says in a parallelogram, opposite angles are congruent. So we just proved opposite sides are congruent. So far we know this about those parallelograms. But now this theorem tells me opposite angles. So opposite angles are going to be the diagonal ones from each other, like this. Now there is a proof for this. We can prove it. I'm not going to be that mean because this proof is going to be about 18 steps to be fully rigorous. Okay. I say it's going to be about 18 steps, but we've already done about 16 of those steps. So we're going to change step number. I got to go back and look at step number. Instead of having step 8 here, that's the only thing we're changing. Step 8, So we had shown, if I redraw this piece in real quick, we had shown this. The other CPC-TC piece, I used highlighter for whatever reason, we're going to say that angle D is congruent to angle B by CPC-TC. Then you are halfway done with the proof. Next, you'll repeat the proof with drawing segment BD instead of AC. All that's going to do is give you two new triangles, right? You're now going to have these triangles. You're still going to find alternate interior angles, and then these angles by CPC-TC. It's the exact same proof. So they're longer, but it's the same repetitive process. So I'm not going to go through all of those steps, but if you want extra practice on proofs, that's something you could practice because you should be able to get that same answer. Now these next two theorems are a little bit slightly different, but I feel like they're pretty useful. So consecutive angles theorem, we referred to consecutive interior angles before as same side angles. So same side angles theorem says that same side angles in a parallelogram are supplementary, not congruent. This hopefully makes sense because we still just have parallel lines cut by a transversal. So if I'm looking at AB being parallel to DC first, and that's my transversal, these two sides have to be supplementary because they're same side interior angles. This is what our warm-up question was. Now, angle A is also congruent to angle C, and we know these sides are also parallel because it's a parallelogram. So if these two sides, or that side, DC is my transversal, angle D and angle C are same side interior angles and need to be supplementary. You're just doing parallel line theorem. All those theorems. Again, just more than one set of parallel lines. Because angle B is the same as angle D. The diagonals theorem says the diagonals of a parallelogram bisect each other. What that really means is the diagonals have the same midpoint. So that's what that means, but we have to be careful about reading that and understanding what it's saying. Because if they bisect each other, that does not mean the diagonals are the same length. So VZ, ZX are going to be the same, those lengths, because Z is in the middle. YZ and ZW are going to be the same length because Z is in the middle. But that distance from Y to Z, this could be 4, like that. So they're not all the same distances. Okay, there'll be a special case about that in the future, but for any parallelogram, the best we can say right now is that the diagonals bisect each other. They have the same midpoint, meaning they both go through the midpoint of the other diagonal. So when we are going to prove that, this proof is also a little bit longer. I believe I'm going to do it in 9 steps. So don't write 2 super huge. So I'll start with statements and reasons. Our first statement is just that ABCD is a parallelogram. It doesn't actually say that anywhere, but because that's all the notes are about today, I'm telling you that it's a parallelogram. So because it's a parallelogram, we know that AB and CD are parallel to each other. Segment AD is parallel to segment BC. That's the definition of a parallelogram. So AB and CD are parallel, and then these things are parallel. Okay, that's just my first initial, just go for it. Now, I can kind of start to think about what's going to happen. So I already mentioned before, when in doubt, try to prove triangles are congruent. There are a whole bunch of triangles in here. Okay, there's the 4 small ones, and then you've got overlapping ones to make bigger triangles. There's a lot of options. You're going to pick 2 that you want to try to prove are congruent. That's always going to be our goal. So try to prove triangles are congruent. Use CPCTC. So what I'm going to do is I'm actually going to pretend these sides don't exist. You could do the same proof with small changes by pretending that AB and DC, those sides don't exist. Because what I'm focused on are triangles ABE and triangle DEC. I can say in step 3 that segment AB is congruent to segment DC, because we're still talking about a parallelogram, even though we're pretending these things don't exist. I'm just doing that so I can visualize these triangles better, but this is still a parallelogram. And one of the first theorems we talked about today is that opposite sides in a parallelogram are congruent. So there, I've got 2 triangles and I've got a set of sides. Now you can do this a few different ways. I'm going to do one way, but again, there are multiple ways to do this problem. The first one that I'm going to do is the thing that always jumps out at me, the thing I always look for are vertical angles, and I have vertical angles here. So I could say that angle AEB is congruent to angle DEC because vertical angles are congruent. That's always true. You can get by without doing this step by doing what's going to be step 5 twice. I'll show you what I mean by that in just a second. So step 5, we're talking parallel lines cut by a transversal. I'm going to look at this transversal right here from D to B. Parallel lines cut by a transversal. I can't say angle B, even though I'm pretending this isn't here. I have to say that angle AB, and then you could say E or D, it does not matter. I'm going to stick with angle E just because that's what's in my triangle. It's going to be congruent to angle CDE because if parallel, then alternate interior angles are congruent. That's my second set of angles. Now when I said you could have done this one twice, you could have also looked at this as a transversal, then you would have been able to get angle BAE is congruent to angle DCE instead. So you could do that twice in step 5 because they have the exact same reason, then you'd be able to eliminate step 4. But now I'm able to say these triangles are congruent. So triangle, and I'm going to go ABE for my first one. Remember, the first order doesn't really matter. The second one does. So I went A to B to E. So I went from the one that I don't know anything about to 2 marks to 1 mark. So CDE would be my next triangle. And my reasoning is angle, angle, side congruence. I don't have the side between the angles, so I had to go angle, angle, side. So my next step is always going to be CPCTC for my reason. And what I'm trying to figure out, remember, I'm proving the diagonals theorem, which said diagonals have the same midpoint. So I need to prove that YZ and ZW are the same, or VZ and ZX are the same, but obviously with different letters in this instance. So what I want is segment AE is congruent to segment CE, AE and CE, and also segment DE is congruent to segment BE. That's not quite enough to say that I'm done. Okay, I have 2 more steps. So step 8 tells me that E is the midpoint of segment AC and segment DB, because that's the definition of a midpoint. And now we're functionally done, right? Because this theorem says show that the diagonals have the same midpoint. But the theorem technically says that the diagonals bisect each other, so we need to actually say that to be officially done. So step 9 AC, segment AC and segment DB bisect each other. And my reasoning is the definition of, this is one we haven't used in a while, but definition of a segment bisector. We typically are using the angle bisector. Now we're talking the definition of a segment bisector. So if you just wrote definition of bisector, I have to count it wrong because I'm not sure if you're talking about an angle or a segment. So make sure you're being specific. All right, and then as you can see, as I already kind of started writing over it, your homework is a worksheet. I hope everybody has a great day, and we'll talk to you guys later.